In this one, we're gonna talk about packed structs and why they are unpacked by default, the structs. It's gonna be quick, but it's a bit counterintuitive. Like when I first learned this, I was a bit confused by it. So you can see here in my example that I have a struct foo that contains an 8-bit integer, a 32-bit integer, and a 16-bit integer. And I create an instance of it, set it to some values, filled with 1 is in hexadecimal, 2 in hexadecimal, and 3 in hexadecimal. And then I print the size of the struct. And what you could guess is that you have 1 byte here, 4 here, and 2 here. So you would guess the struct should be 7 bytes, but actually, if you run this, like so, you can see that it's 12 bytes. And that's very, very strange. So what the compiler does is to optimize the way the memory in the struct is loaded by the CPU. It will add some padding between the field. So here there will be padding, and I think here maybe there will be padding, or here. I think it's a bit compiler dependent, and I'm not too familiar with how the inner workings work, but that's how it is. And the reason why there is padding is, for example, on a CPU, you have instructions to load as much bits as the CPU is. So, for example, if you have a 32-bit CPU, you have an instruction that is to load 32-bit at a time. And if so 32-bit is 4 bytes, and if the address you're trying to load is not 4-byte aligned, so if it's not a multiple of 4, it will have to do 2 loads for it. See, if like your 4-byte integer is on not aligned, it will have to fetch the memory that is on the first part, fetch the memory that is on the second part, and then remerge the two. Or at least that's what I read when I used to learn about this topic. So I think that's why they do it. Anyway, we can also just here print the bytes. So I just cast it as an array of a pointer to an array of bytes, and I just print every byte in it to see how it looks under the hood a bit. So you can see that in my case, the byte is a first, but then there is 3 bytes of padding, then there is the 4 bytes integers, and then there is the 2-byte integers, and then there is more padding at the end. And this number is a bit random, so if I run it multiple times, you can see that this byte is a bit random, since it will never be read in a normal program where you're not doing weird stuff like this. And so, yeah, that's just optimization done by the compiler. And so, yeah, you're basically wasting, in my case, it will be 5 bytes as a trade-off for faster load on the CPU. And you can fix this, for example, by reorganizing your struct by putting the largest element at the top. That's usually what I do. So I think here you can see that now our struct is only 8 bytes, and it still had 1 byte of padding at the very end. But let's say you're not able to do that. Yeah, let's go back to this example. You can also force the compiler to pack the struct, so to not add padding between the field, by adding underscore attribute, like so, 2 underscores after rule, and packed, with 2 sets of parentheses. It's a very weird syntax, and it's compiler specific. So I know it works in GCC and Clang, this one, but I don't know about any other compilers. But if you use that, you can see that now it has added no padding whatsoever, and the size of the struct is what you would expect. And the main reason why you would want to do this, I wouldn't recommend doing this on every single one of your structs, because you might think, yeah, I'm gonna save some memory, but I don't know. Oftentimes you can just rearrange the fields, or yeah, it's not really worth it, for the loss of time you lose because you need to do 2 loads every time. But for example, a case where it's very useful is when you're reading a binary file or binary data from network, and it's just packed because the protocol is set that way. It's really nice to have just attribute packed so that you can just read the byte directly into the struct and not have to worry about the padding introduced by the compiler. So yeah, that's about it. I hope you learned something from it, and yeah, see you in the next one.